Alright, so in this video we're going to go over some kinetics material. I'm just going to straighten out the camera here and the paper. So that's basically our plan. So let's just go ahead and jump right into it. So it says, given the following balanced equation, determine the rate of reaction with respect to hydrogen. Okay, so we have nitrogen plus 3 hydrogen is going to yield 2 ammonia. It's a very industrially important reaction. Okay, so basically, if we look at a general reaction, little a A's yields little b B's. All right, where little a is the stoichiometric coefficient and big A is the chemical A. All right, and same for B. And we notice that these are products and reactants. We can write the rate expression like this. Rate equals negative 1 over little a. Why negative? Because A is a reactant and we can reasonably expect that the reactant will be used up. 1 over A, because if it takes 5 A's to do a reaction, the rate with respect to A is going to be 1/5 the overall rate of the reaction, because 5 of them do one reaction. Delta concentration A, don't forget that if you put a chemical in brackets, in this case A, which is not a real chemical, if you put it in brackets, it means concentration over delta T. And this is often a rate. Okay, this is a rate, delta concentration over delta T. For B, it's the same thing, except it's positive. Why? Because B is a product, and we can reasonably expect we will get more product as the reaction occurs, but it's still 1 over little b, the stoichiometric coefficient with respect to B, delta concentration of big B, the chemical, over delta T. In your randomized online homework questions, questions 2 and 3 specifically, and these are also available in the other videos. Similar questions are available in videos that you can look for on the equivalency table. You'll actually have to solve these things out, all right? But for this one, we just need to write the reaction. In the interest of time, this thing's already 17 questions. I don't want to do one where I solve it out. I just want to remind you of the equation. So let's take a look here. If we're looking for respect to hydrogen, it's negative 1 over 3. Why negative? Because hydrogen is a reactant. Why 1 over 3? Because there's 3 hydrogens in the reaction. Delta concentration of H2 over delta T. Okay, this is the rate of change with respect to hydrogen. Again, we're not plugging in any numbers. If you go over the randomized homework questions 2 and 3, there you actually have to plug in the numbers to find the average rate, or find the average rate with respect to one when you have the average rate with respect to another. All right, it says, give the characteristic of a second order reaction having only one reactant. So if it's a second order reaction, the rate of the reaction is proportional to the square of the concentration of the reactant. Remember that in the rate laws, rate equals K, we'll call this reactant X, although X doesn't of course really exist, concentration of X squared. Because it's a second order reaction, it's squared with respect to X. Since it's only having one reactant, we know that it's squared with respect to X. Note that if you had a reaction with 2 reactants, we don't in this case, but if we did, we could have the rate equals K, concentration X, concentration Y. This would also be a second order overall reaction, okay? So this could be the rate law for x plus y yields z, or this could be the rate law for x plus y equals z, and we could experimentally determine which one that it is. But in this case, because it only has one reactant, we know that it has to be proportional to the concentration of the square of that only reactant, because if it's overall second order, it has to also be second order with respect to that reactant. Also notice there's no products in the rate law, okay? The rate law only has the reactants, because the concentration of the reactants can, and often do, affect the rate of a reaction. Number 3 says, what is the overall order of the following reaction given the rate law? Well, if we look here, rate equals K, concentration X, concentration Y. Note that the stoichiometric coefficients, or said another way, the fact that this is first order with respect to X and first order with respect to Y, these are not the stoichiometric coefficients. We happen to have one X and we happen to have 2Y, but it's only first order with respect to X and first order with respect to Y. Note that if there's no number here, we know that it's first order. If it's 0 order, X or Y wouldn't even be there, because it'd be concentration X to 0, which is just 1, so that wouldn't even be there. And if it was second order, it would say squared. So that's basically that. But also notice they are not the stoichiometric coefficients. Why are they not the stoichiometric coefficients? Because we don't know the mechanism of this reaction. So we need to experimentally determine how the changing the concentration of X and the concentration of Y affects the rate of the reaction, or said another way, we need to learn something about the mechanism of the reaction in order to find the rate law. And then on one of the subsequent questions, it might be the next question, we'll actually see one way that that could be accomplished. But to answer this question, it's first order with respect to X. It's first order with respect to Y. What is the overall order? The overall order is second order. You simply add them together. So it's 1 and 1. You just add them together, and it's overall second order. All right, so this question is a lot of work. It says, determine the rate law and the value of K for the following reaction using the data provided. Now, this is just one example. There's a similar example in the randomized online homework. It's really important that you practice this because there's a lot of steps and it's really easy to get confused and, miss something, okay? So remember, like we talked about in the previous question, the reaction orders are empirically determined, which means you actually have to do the experiment and try it out. This is one way to determine the rate of a reaction. Said another way, it's one way to learn something about the mechanism, or maybe what's the slow step of the mechanism, and so on and so forth. So rate equals K, in this case, concentration of NO2 to the some power, I'm going to call it M, concentration of O3, ozone, to the N. Okay, this is the general form of the rate law. You cannot assume that M is 1 and ozone is 1, N is 1, because there's one of these and one of these. Why not? Because this is the overall reaction, and we don't know the mechanism of the reaction, so we don't know what the slow step is, what is actually bouncing into each other and reacting, or something's falling apart, or whatever the case may be. We don't know what that is until we do a study like this. Okay, so what did this person do? Well, this person found that if they use 0.1 molar of this and 0.33 molar of this, this is the initial rate. So basically, this is the initial slope of the line for measuring the change in concentration. Then for trial 2, they basically, I'm going to label these 1, 2, and 3 so that I can refer back to them. For trial 2, you'll notice they doubled the concentration of the O3 and they looked to see what happened to the rate. Now, if you've done a bunch of these, you can realize that it's got to be first order with respect to ozone, because if you double the concentration of ozone, you double the rate of the reaction exactly, okay? It's not usually this nice, all right? So experimentally, it doesn't usually work out this nice, but here with made up numbers, okay, you can see it exactly there. Now, if we look at the here, in this case, they kept the concentration of the ozone the same in trials 2 and 3, but they made the concentration of NO2 2.5 times as much. So now it's 2.5 times as much, this concentration. Well, what happened to the rate? If you notice, this is also exactly 2.5 times as much as this. So this one, it kind of works out perfectly. So if you've done a bunch of these, you don't actually have to do a bunch of math, but oftentimes you do, because if it's not first order, it's not always as obvious. So let's look at how we're going to do this. Well, what we're going to do to actually determine these variables that we've done is we're going to write this out for 2 different trials. And which trials are we going to do it for? Well, if we want to find with respect to N, which I'm going to find first, even though it comes second because it's the first 2 trials, this you have to look at the part where NO2 concentration is constant and the O3 concentration changes. Notice you wouldn't want to compare trials 1 and 3 because both things change. If both things change, we don't know which thing changed the rate. So we have to change one thing at a time in order to see how that affects the rate. So you have to design your experiment carefully. So what are we going to do? Well, I'm going to write this rate expression out to find N for trial 1, and I'm going to write it out again for trial 2. So for trial 1, rate equals K, this to the M, this to the N. Well, let's plug in what I know. Well, I know the rate. So for trial 1, the rate is 1.42 equals, now I'm going to write K, I don't know K. Concentration of NO2, I do know, 0.10, and I know that that's to the M. I don't know M. Okay, so I don't know this. But I do know the concentration of O3, it's 0.33, and I don't know n. All right, I'm going to repeat this for trial 2, where I'm going to put in 2.84 equals k. I still don't know k. I do still know NO2. It happens to be exactly the same. That's important, okay? We need to compare a trial where we only change one thing. And specifically, if we want to find N, we need to look where the concentration of ozone has changed, O3. And then for concentration of O3, in this case, it's 0.66 to the N. Now, if you look here, you have 3 variables, K, M, and N. And you only have 2 equations. In math, they'll tell you that you can't solve that, right? Because you'd have to have 3 equations and 3 variables in order to solve it out. But in this case, you actually can, because you don't have as many variables as you think, because you've now made a constant. The 0.1 to the m is constant in both trials. This makes sense experimentally because we want to change the concentration of one thing, in this case ozone, and not the other thing, so we can see which one affects the rate, right? Does the O3 actually affect the rate? Well, let's change that and not change this, and then we'll know. But it also makes sense mathematically because now you have a constant. This is no longer a variable because it's the same in both equations. What's the easiest way to solve this? It's to divide through, okay? Divide these two things by each other. So what do you get? Well, you get 1.42 over 2.84 equals k cancels, 0.1 to the m cancels, and we get 0.33 to the n over 0.66 to the n. Simplify, so just actually do this, which is exactly half, 0.500 equals, you can simplify this as well. This divided by this, all to the n power, which in this case, it's exactly half. So 0.500 to the n. Again, these are made up numbers, so they come out perfectly. Okay, now in this case, what you would normally do to solve this is take the log of both sides. Why? Because a logarithm is exponential, so therefore the exponents become multiplicative. Said another way, if you take the log of 0.5, it doesn't equal the log of 0.5 to the n, it equals n times the log of 0.5. Then you can solve it. But in this case, that's completely unnecessary. Why? Because you have 0.5 equals 0.5 to the n. N has to equal 1. Because that's the only way that those two things could be equal, right? This has to be 1. We have to raise this to the 1. So another way, it's just 0.5, because 0.5 equals 0.5. Okay, so you could take the log of both sides, but it's not necessary in this case. All right, let's repeat this and try to find m. Okay. The trick here is to find which 2 trials to compare. So we want to change NO2, but we want to keep O3 constant. So if we look here, O3 is constant in trials 2 and 3, and the concentration of NO2 changes in trials 2 and 3. So these are the 2 we want to compare. Specifically, we want to write out 2. Well, 2, K, or excuse me, not K, but the rate is equal to 2.84 equals K, I don't know K. Concentration of NO2, hopefully you can see that, concentration of NO2 in trial 2 is 0.10 to the m, and the concentration of O3 is 0.66 to the n. And because these are getting long and complicated, I'm not putting units in here. Okay, you probably noticed that from before. I should have said it before. All right, for trial 3, do the same thing. Okay, plug in what you know. Well, I know the rate. It's 7.10, so I'm just plugging that in. I still don't know K, so I'm just going to put in a K. I know concentration of NO2, it's now 0.25 to the m. And I know the concentration of O3, which is 0.66 to the n. Divide these through. I'm running out of space, so I'm going to put it over here. And what you get is 2.84 divided by 7.10 is 0.40. I'm going to add a 0 equals 0.1 divided by, or excuse me, K cancels. 0.1 divided by 0.25 is 0.400, all to the m, and then 0.66 to the n, 0.66 to the n, it cancels out. Same as before, since these are exactly the same number, I don't need to take the log of both sides. M, excuse me, m, not n, equals 1. All right. So now I found the values of n, m, and n. I also know rate, concentration of this, and concentration of this for each of the trials. So I want to plug in one more time. Why do I want to plug in one more time? Because I want to find K. It makes absolutely no difference which trial you pick. I'm going to pick trial 1 because it comes first. But if you like, pick trial 3. It makes no difference, especially with these very perfect numbers. It's not going to make any difference at all, like literally no difference, okay? With experimental data, it might make a slight difference, but in this case, it's not going to make a difference. So let's take a look here. I'm going to plug in trial 1. Well, for trial 1, what is rate? Rate is 1.42. I'm again going to ignore units because this is already complicated math, equals K, that's what I'm trying to find. Then 0.10, that's going to be to the M. But I just found M. M is equal to 1. So that's going to be to the 1. I'm not going to write a 1 there because anything to the 1 is just the number. All right. And then now concentration of O3, which is 0.33. And that's going to be to the n, but n is also equal to 1. So again, I'm not going to write a 1 there because 0.33 to the 1 is just 0.33. Now solve for k. Just multiply these two together and then divide by 1.42 by the 0.033 that you get. When you multiply these two together, and you get k is equal to 43 per molar, okay, per second. All right, so that's basically what you're going to get when you do this. And, okay, if we look here, B, rate equals 43. I might have said 0.43, but I wrote down 43. 43 molar per second, per molar per second. Concentration NO2 to the 1, concentration of O3 to the 1. So choice letter B is the correct answer. These are a ton of work, okay? On the homework, you may not have gotten M and N to come out perfectly, and you may have had to do logarithms, and there are videos that show that, but in this case, you know, they come out perfectly, okay? All right, number 5 says, for a reaction that follows the general rate law, rate equals K, concentration A to the 1, or no number, concentration B squared, what will happen to the rate of the reaction if the concentration of B is increased by a factor of 3? First of all, this is an overall third order reaction where you have a 1 here and a 2 here. These are exceedingly rare, but we basically have this here. So if we look at B, it says the rate is dependent on the concentration of B squared. So if we triple the concentration of B, the rate will increase by a factor of 9. Why? Because 3 squared is 9. So if it's second order with respect to B, when you triple the rate, you'll get 3 squared or 9 times faster increase in the rate. Note that if you tripled the concentration of A, okay, and not B, the rate would increase by 3 times, okay, because it's first order with respect to A. So it depends on which one you're asked about for how much it's going to increase the rate of the reaction. All right, number 6 says, how many half-lives are required for the concentration of the reactant to decrease to 25% of its original value? So this happens to be an even number of half-lives. So for the first half-life, you will have half left. For the second half-life, you will have half of half left, which equals 25%. So after 2 half-lives, you'll have 25% left. If you want a third half-life, you'd have half of 25%, which is 12.5%. And if you want another one, you'd have half of 12.5%, okay, which is what, 6.25%, so on and so forth for the number of half-lives in order to that will pass. We'll do a question a little bit later on where you don't have an even number of half-lives, and then math doesn't work out quite this nicely. All right, it says, what data should be plotted to show that the experimental concentration data fits a second order reaction? Okay, this is something you just have to memorize, okay? But if you are given the second order rate law, you can figure it out from that. So the second order rate law is 1 over the concentration of some A, or maybe some X, at T equals KT plus 1 over the initial concentration of A, 0. Sometimes these are X's, sometimes they're A's. I'm going to use A here. Okay, this is the experimental second order rate law. If you plot this on a line, Y equals mx plus B. Okay, so the Y value is 1 over the concentration of the reactant, which is A. M is the slope, is K. X is time. Okay, so that's what you want on the x-axis, plus B, 1 over the concentration of A. This is the y-intercept. Okay, so that's basically how it works. So 1 over reactant concentration versus time is going to be your second order rate law. Notice that if you have a first order integrated rate law, which we'll use in a little while, ln of the concentration of A, 0, equals negative kT plus ln of the initial concentration of A. Sorry, this should be A at some t. I made a mistake there. All right, so the ln of concentration of A at t equals negative kT plus ln of k0. Y equals mx plus B. In this case, the y value should be ln of the concentration of A as time goes on. The x value should be time. Said another way, the ln of the reactant concentration versus time, this is your first order reaction. I'm not going to write out the zero order reaction, but at the concentration versus reactant versus time, this is your zero order reaction. You're actually going to do this in the lab, and you're going to make the 3 plots looking at the blue dye concentration versus time and figure out what is the order of the reaction based on which one gives you the straight line. So this is just something you have to know, but you can figure it out if you're given the integrated rate laws without having to memorize it. Just remember y equals mx plus b, and it's right in the right order. You don't even have to rearrange anything, which is pretty nice. All right, number 8 says, the rate constant for a second order reaction is 0.54 per molar per second. What is the half-life of this reaction if the initial concentration is 0.33 molar? So each of the reactions have a half-life equation. When I say each of the reactions, zero order, first order, and second order type reactions have a half-life equation. For the second order reaction, the half-life is T1/2 equals 1 over K times the initial concentration of A. Second order half-lives, and similarly zero order half-lives, are relatively not as useful because if you notice, they have the initial concentration of A in them. For a first order reaction, the half-life is 0.693 over K. That's very useful because the first half-life and the second half-life are exactly the same, and the third half-life and the fourth half-life and the fifth half-life, they're all exactly the same. In this case, the second half-life is not the same as this half-life, okay, because the concentration of A0 will be different. So therefore, you're going to have a different half-life. So it's not quite as useful, but we can still solve for it. All right, so it's 1 over 0.54 per molar per second times the 0.33 molar, the initial concentration. So I just simply plugged in K, I simply plugged in the initial concentration, and we get 5.6 seconds. Okay, so these questions aren't too bad. They're much harder when you're given a half-life and then you're asked for how much is left, and we'll do a question like that at the end. All right, so question 9 says, the combustion of ethylene proceeds by the following reaction. When the rate of disappearance of O2 is 0.28 molar per second, what is the rate of appearance of CO2 effectively is what it says. So let's take a look at this. So in question 1, I mentioned that you could review some of the randomized homework, and one of them is a question just like this with a different reaction. So let's take a look at this. So we have to remember that if you haven't done question 1, do that before you do this one. Okay, that with respect to O2, what we need to do is the rate is negative 1 over 3, 1 over the stoichiometric coefficient, delta concentration O2 over delta T, equals the rate of appearance of CO2, use its stoichiometric coefficient, it's positive 1 over 2, delta concentration of CO2 over delta T. Okay, so this is basically what you have. Now, this there's a couple things we need to know. The first thing is this is negative because we're losing 0.28 molar per second because it's disappearing. The second thing we need to know is this whole value, and this is what we're trying to solve for, this whole thing, delta concentration CO2 over delta T. This is the rate of appearance, in this case of CO2, or disappearance of O2. It's not the concentration of O2 over delta T. There is a question like that in the randomized homework where you actually solve this out with the given two concentrations in one or two times. All right, sometimes you're given like the initial time and the final time, and sometimes you're getting given over 40 seconds, so you know delta T, the change in time. Okay, but in this case, this is this whole thing. So negative 1 over 3 times negative 0.28 molar per second. Okay, that should be a minus 1. Okay, equals 1/2 times delta concentration CO2 over delta T. So multiply these out. You do need to plug this in as a negative, or just realize that the CO2 has to be positive because it's a product and because it says the rate of appearance. So that implies it is positive. That's just like the rate of disappearance implies that this is negative. You'll also notice there's no negative answers, so that's really fine. So take this one, basically divide it by 3, and then multiply both sides by 2, and you'll get the right answer when you do that, which is 0.19 molar per second. Okay, which is this one. Okay, so that is basically how it works. You'll notice that this rate is faster for O2 because 3 of them makes a reaction. So each one is going to be faster than for CO2 because 2 of them makes a reaction. So for each one, it's slower. All right, question 10 says, the first order decomposition of N2O5 at 328 K has a rate constant of this. If the initial concentration is 2.88 molar, what is the concentration after 12.5 minutes? All right, this is a little bit tricky. First things first, we don't need the temperature. That doesn't matter. I mean, it matters because it'll change if you change the temperature, but this one's at constant temperature, so we can basically just ignore that. The other thing, and this is a little bit tricky, the rate constant is 1.7 times 10 to the minus 3 per second, and we want to know after 12.5 minutes. You have to either put this into minutes, which I probably wouldn't do. I would put this into seconds. That's probably the easier way to do it because I just multiply that by 60. So if I take the 12.5 minutes and I multiply by 60 seconds in a minute, I find that there are 750 seconds. Now we have to use the integrated first order rate law. This is the usefulness of the integrated first order rate law. It allows us to predict how much is left after a specific amount of time. Okay, the overall rate law allows us to predict things like what will happen if we double the concentration of something, or is the thing even in the rate law at all? Okay, but it won't allow us to predict how much will be left after a certain amount of time. The integrated rate law is good at looking at those things. Okay, so that's what we want to use. So in this case, ln of the concentration of N2O5 after some time equals minus kT plus ln of the concentration of N2O5 initially. Okay, and that's what the little 0 means, initial, and the little t means after some time. Note that this is first order integrated rate law. This would be different. It'd be 1 over the concentration of N2O5 at some t if it was the second order rate law. Or it would just be the concentration of N2O5 at some t if it was the 0 order rate law. So you need to know which one to use. In this case, because it's first order decomposition, make sure you're using the first order integrated rate law. Now let's plug in. Okay, so the ln of the concentration of N2O5 at some t equals minus K. We know K. 1.70 times 10 to the minus 3 per second times 750 seconds, not 12.5 minutes, plus the ln of the initial concentration of N2O5, which is 2.88. Okay, now when you simplify this, if you take the ln of 2.88, you get 1.058. And then you multiply these two things together, you get negative 1.275. You then add those two things together, and you find that ln of the concentration of N2O5 at some t is equal to negative 0.2175. 2. Okay, so basically multiplied these two things together, got negative 1.275, took the ln of this on a calculator, of course, and you get 1.058. Okay, now we simplify to this. Now, how do you get rid of the ln? Well, you take e, okay, or in your calculator, shift ln. Okay, this is Euler's number, so this is the base of this. If it was a log, this would be 10 to the power, but in this case it's e 2.7 something, I think. Okay, that you're going to take to the power, and of course if you take the e to the ln, you have to take the e to this number. E to the ln just gets rid of it, so you just get the concentration of N2O5 at some t equals e to this number, which you're going to do on your calculator, and you're going to get 0.805 molar. Okay, so that is choice letter A. Make sure you know how to use your calculator to do these things. On some calculators, you put the number in and then you hit shift ln. On other calculators, you hit shift ln and then put the number in. So just practice with the particular calculator that you have and make sure you know how to use it. If you don't, come to homework help or office hours and we'd be happy to show you as best we can. There's basically two major types of calculators that people have. So usually, like, I know how to do it, but occasionally you get some weird brand of calculator or some unfamiliar, it's not weird, brand of calculator, and it takes me a few minutes to figure it out. But usually there's one of two ways of doing it. All right, let's skip to the next question. All right, it says the second order decomposition of NO2 has a rate constant of 2.55 per molar per second. How much NO2 decomposes in 4 seconds if the initial concentration of NO2 in a 1 liter of volume is 1.33 molar? Now, this has got a lot of extra math in it that's a little bit unnecessary. And if you look at the question or the answer key, you'll see I selected the wrong answer the first time, and I'll show you why. This one tripped me up a little bit. All right, so let's take a little bit of or take a second and go over this. So first things first, in the previous question we did first order integrated rate law. In this case we're doing a second order integrated rate law. Okay, the good news is our rate constant, it has a time unit of seconds and our time is seconds. In the previous example we had to convert minutes to seconds, which is an easy mistake to make if you forget to do that, but in this case we don't have to do that, so we have the same thing. We need to know their integrated second order rate law, so we need to use the right one. So in this case it's 1 over the concentration of NO2 at some t equals positive kT plus 1 over the concentration of NO2 initially. Okay, so this is the second integrated second order rate law. This was the integrated first order rate law, so just make sure you use the right rate law. Okay, the right integrated rate law, I should say. All right, now what do we need to do? Well, what we need to do is we need to plug in what we know. Well, 1 over the concentration of NO2 at some t, that's what we're trying to figure out. So 1 over the concentration of NO2 after some t is what we're trying to find. K, we know, 0.255 per molar per second times 4 seconds. I guess I should put 4.00 seconds plus 1 over the initial concentration of A, or in this case NO2, which is 1.33 molar. All right, so this you could just solve out. This times this plus 1 over this. All right, and you get 1 over the concentration of NO2 at some t equals 1.77 molar to the minus 1. Now, how do you solve this? What you have to do is take the reciprocal of this. So the concentration of NO2 at some t is going to be 1 over 1.77 molar to the minus 1. So just take the reciprocal, 1 divided by this, and then flip this one upside down as well, and you get the concentration of NO2 at some t equals 1 divided by 1.77, which is 0.56 molar. Then, because I rush and I make a lot of mistakes, I just picked 1.57, or 0.56, excuse me, not 1.77, 0.56 moles. All right, a couple things. because we have 1 liter of volume, molar and moles is the same. Okay, it asks for how many moles are left, but it doesn't make any difference because it's 1 liter of volume. So said another way, 0.56 molar is 0.56 moles per liter. Well, if you only have 1 liter, it's also 0.56 moles. It's the same, but it's not the right answer. Why? It asks for how much NO2 decomposes. This is the current concentration of NO2 after some time, right? This after specifically the 4.00 seconds. So this is what's left, not how much decomposed. If you want to find how much decomposed, you need to take the 1.77 molar and subtract the 0.56 molar. And when you do that, you find that 0.77 molar is gone. Or for every liter, in this case it's 1 liter, 0.77 moles have disappeared. Okay, so you have to read the question carefully, okay, which I did not, and pick the wrong answer. So make sure you're reading the questions carefully. Also make sure you can solve these mathematically. The math is challenging here, and it takes practice, and it's really easy to make a mistake. So you gotta practice and make sure you're getting them to come out correctly. All right, it says, for a reaction, what generally happens when temperature is increased? So after the last two problems, which were a ton of math and quite complicated, we end up with a slightly easier one. All right, generally speaking, when you increase the temperature, the reaction goes faster. Okay, so the rate of the reaction increases. This also means there's an increase in K. So rate equals K times the concentration of X to some m power. Let's assume there's only one reactant in this reaction. The concentration of X and the reaction order with respect to X are not going to change when you change the temperature. These are constant. So the rate increases, therefore the K also increases. As rate increases, K must increase, so an increase in K occurs, which results in a faster rate. They're directly proportional, if you want to put it that way. They're on opposite sides of the equation. You can, so they're directly proportional, or you can just think of it as, if this goes up, this also has to go up because this part is constant, right? Obviously, changing the temperature is not going to change the concentration of X. Maybe not obviously, it's also not going to change the reaction order with respect to X. All right, another complicated math problem. Whoops, I don't want that. All right, it says a reaction is followed and found to have a rate constant of 3.36 times 10 to the 4 at 344 K and a rate constant of 7.69 at 219 K. Determine the activation energy for the reaction. So this is the Arrhenius equation. Okay, this is ln of K2 over K1 equals EA over R. Note that this is R is 8.31 joules per mole K. It's not the one you're used to, 0.08206, because that's liter atmospheres per mole K, and 101.3 joules is a liter atmosphere. So it's the same constant, it's just different units. We took the 0.0821 and multiplied by 101 basically, and we get 8.31. Okay, then it's 1 over T1 minus 1 over T2. These things are a pain in the neck to solve. You have to practice this, okay? These are not simple to solve out. They're really not simple if you have to solve for a T or a K, okay? The T's are the worst in my opinion, but they're not as simple to solve. So make sure you practice a couple of these, all right? There's at least one on the homework. So what are we gonna do? Well, the first thing I usually do when I'm doing these kinds of problems to try to orient myself is pick a 1 and a 2. This is my 1 and this is my 2. Okay, why do I do that? Because I know this one goes with this temperature and this one goes with this temperature. It makes no difference which one is 1 or 2. You'll get the exact same answer whether you plug in this one is 2 and this one is 1. It doesn't make any difference, but it does matter that this K goes with this temperature. So if I plug this down here, I need to plug this temperature here. If I mess that up, I will get the wrong answer. So said another way, if I put this one here and this one here, I will get the wrong answer. That's why I like to label them so I know which goes with which. Now I can plug in. So I don't have a lot of space. I guess I took up too much space with this one. All right, so the ln of 2, I'm going to call it as 7.69. I'm going to leave the units out here just for clarity, okay, because they're the same and it's a proportion, they're going to cancel out. And then over 3.36 times 10 to the 4th. All right, so this is my 1, and so I put it in the bottom, and this is my 2, so I put it on the top. That's why I like to label them. Equals EA, that's what I'm trying to figure out. R is 8.31, that's joules per mole K. Note it's joules, and this is kilojoules, so we're going to have to take our answer and divide by 1,000, okay, times 1 over T1, okay, I remember this one is T1. I'm going to leave out the units again. 344 minus 1 over T2, which I remember is 219. All right, this is why it's a good idea to label them. All right, now we need to divide these out and subtract, okay, then take what you get and divide it by 8.31. When you simplify this, okay, you get negative 8.382, which is just this divided by this, and then take the ln of your calculator, equals EA over 8.31 times negative 1.659 times 10 to the minus 3, which is this whole thing. Okay, now divide that by 8.31, and what you get is negative 1.6, negative 1.966 times 10 to the minus 4 EA. So I just took this number and divided by 8.31, and I got this number times EA equals the same number, negative 8.382. Okay, then divide. Divide by this, divide into that one, and you get EA is equal to 42,000 joules per mole, which is 42.0 kilojoules per mole. We have to divide it by 1,000, so the answer is choice letter E. This math is a pain. Again, it's especially a pain if you have to solve for T1 or T2, and it's no fun if you have to solve for K2 or K1 either, but I think the worst ones are the temperatures. Okay, so make sure you practice a couple of those. All right, oops. It says, given the proposed mechanism, predict the rate law for the overall reaction. So remember that mechanisms are elementary reactions, which means the NO2 is actually bouncing into the Cl2 to form the NaCl and the Cl. So these are actually colliding with each other. Said another way, the stoichiometric coefficients are the reaction orders. It's first order with respect to NO2 and first order with respect to Cl2. In this case, it's first order with respect to NO2 and first order with respect to Cl, because these are, again, elementary reactions in the mechanism. Well, which step is going to be important in the rate, the slow one or the fast one? The rates of reactions are based on the slow step, because they're the rate limiting step, or they're the one that determines how far the overall reaction goes. Because the first step is the slow step, this is much easier. Rate equals K, concentration NO2 to the 1, we can use the stoichiometric coefficients, times concentration Cl2 to the 1. Note, we can't use the stoichiometric coefficients in the overall reaction. We have to use them from the slow, elementary, or mechanistic step, because these are not necessarily interacting in the slow step, but we know in the slow step these two things are interacting. Note that this is much more difficult, and you get weird rate laws often if this is the second step is the slow step. And the reason for that is you can't have intermediates in your mechanism. So Cl is not in the overall reaction. But the first step of the mechanism always has reactants in the overall mechanism, because that's all you have. You don't have any intermediates idiots at that point. So I'm not going to go through an example like that. You may have gone through an example like that in class. I usually do go in, when I teach this, go through an example like that in class, but I don't usually put it on a test. I don't know if it'll be on your test or not, but you might check your lecture notes and go through an example where the second step is a slow step, just to make sure you know how to cancel it out. It's basically algebra, okay? In this case, rate equals K concentration NO2 Cl2, which is, be careful, choice letter D. Okay, this one's close, but this is not the right answer. This was if this was the slow step, and this wouldn't be a valid overall rate anyway, because again, Cl is not in the overall reaction. All right, number 15 says, consider the concentration versus time graph of the reaction below. Which compounds is/are represented in the graph. I noticed that graph got cut off here. I forgot to type the end of it. I'm not sure. But anyway, I just added the rest of my pen. All right, so basically we have, this is A, B, or C. We have this reaction. A yields B plus C. And this is the concentration of A, B, or C. And this is time. And we need to determine, is this A only, B only, C only, B and C, or we don't know. It's not enough information to tell us. All right, there's plenty of information to tell us, so choice E is not the answer here. If we notice, we start off with a relatively high concentration, and as the reaction goes, the concentration of whatever's in this graph is decreasing. This means that it has to be A. Why does it have to be A? Because we can only reasonably expect that the concentration of A will decrease. Why will the concentration of A decrease throughout the reaction? We could say it one way is A is a reactant, so we expect its concentration to go down because it's forming B and C. Or you could say another way, the B and C's concentration should be increasing through time as the reaction proceeds and more of them are formed. So if you start with only A, you would start with no B and C, and then it would increase through time. So this has to be A because it's the reactant, and the reactant concentration decreases through time. All right, so I decided to put a little bit harder half-life question on here. It says a first-order reaction has a half-life of 36.3 seconds. How long will it take for 8.27% of the sample to remain? Note that 8.27% is not an even number of half-lives, so we can't just count. If it said how much long will it take for 50% of the sample to remain, it would be 36.3 seconds. Or if it said 100 or 25% of the sample to remain, it would be 2 times 36.3 seconds, which would be what, a minute and 12 seconds, 72.6 seconds, which is a minute 12 seconds. Roughly, okay, 12.6 seconds, I guess I should say. Anyway, that's not the point here. The point here is this is not an even number of half-lives. When you don't have an even number of half-lives, it's a little bit trickier. What you're going to have to use is the integrated first-order rate law, which we're going to call this reactant A. So the ln of the concentration of A at some t equals negative kT plus the initial concentration of A. Okay, now you have two choices. All right, you can use the concentration of A at some t as 8.27 and the concentration of the initial concentration of A as 100. Okay, because you start with 100% and then you have 8.27% left, so you can just use those numbers. It's probably slightly easier mathematically to use them as real numbers and not as percentages. So the concentration of A at some t is 0.0827, so this is a percentage out of 1 or a fraction. All right, and the concentration, I don't know why I did that, the concentration of A initially is 1. This makes the math a tiny bit easier. Okay, it's not a big deal if you use 8.27 and 100. Go ahead, you'll get the same answer. You have to push a few more buttons. Why is this a little easier? Because the ln of 1 is 0, so you can basically just ignore this term. So it's slightly easier to do it. The problem is we can't plug in, because if we look here, K and T are both variables. All right, we know this concentration, good. We know this concentration, good, but we don't know K or T. So we can't plug in yet because we don't know enough information to solve this. We need one variable. We only have one equation. Well, how are we going to find one of these things? Well, it turns out we can find K. We're trying to find T. How can we find K? We can find K from the half-life equation. T1 half equals 0.693 over K. Note that both of these things are tied to the first order reaction. In fact, you can derive this from this, okay? But these are both derived from the first order reaction. If this was a second order reaction, these would be different equations. But it's not a second order reaction, it's a first order reaction. So in this case, if we rearrange this, we find that K equals 0.693 over T1 half. So cross multiply, then divide by T1 half, and you get this equation. So K equals 0.693 divided by the 36.3 seconds, which is equal to 0.01909 seconds to the minus 1. Okay, so now we know K. We know concentration of A at some T. We know the initial concentration of A, and we know K. We can solve for T, no problem. Let's plug in. ln of 0.0827, which again is just 8.27% divided by 100, so out of 1 instead of out of 100, equals negative K, which is 0.01909, okay, and that's seconds to the minus 1, times T plus the ln of A, 0. I'm not going to go ahead and write that because the ln of 1 is 0, so it's just plus 0, so I'm just going to ignore it. Okay, take the ln of this side, and you get negative 2.493 equals negative 0.01909 seconds to the minus 1 times T. Make it with a dot maybe so it doesn't look like an X. Okay, then divide both sides by the negative 0.01909, and you find that T is equal to 131 seconds. So after 131 seconds, we will have 8.27% of this sample remaining. Note that this sample has a very quick half-life. Okay, half of it will be gone in 36.3 seconds. So in 131 seconds, a little over 2 minutes, you're only going to have about 8% left. All right, we finally make it to the last one. It says, consider the reaction coordinate diagram below. So this one is not multiple choice because I didn't want to make it into 5 questions. Okay, so basically instead of making it into 5 questions, I just did it all at once, and I didn't just to make less questions. All right, so let's go through this one. It says, how many steps are in the mechanism? This is a 2-step mechanism. This is the first step. So this, again, is the first step. And this is the second step. So first step, second step. So basically, every time you have a low point is a step. So here to here is 1 step, here to here is step 2. So this is a 2-step mechanism. Okay? How many intermediates are there? This is an intermediate. So when it goes up to a higher point, okay, this is a particularly unstable thing, it then falls to an intermediate. Oftentimes, intermediates are not something you can isolate, so then it continues on to the products. Okay, but there is your intermediate at the bottom of the hump here. So there is 1 intermediate. How many transition states are there? There are 2 transition states. Basically, they're the same number of transition states as steps. Okay, so each high point here is the transition state. These transition states cannot be isolated, so we can't stop this reaction at these points, okay, up here. These are the particularly unstable things. What is the slow step? Well, the slow step is the one with the highest activation energy. So if we look at the first step, the activation energy is this much from here to here. So basically from 10 to roughly 90. Okay, if we look at the second step, the activation energy is here. So roughly, I don't know, 55 up to 75. So this one has an activation energy of around 80 kilojoules, and this one has an activation energy of around 20 kilojoules. So the first step is the slow step because it has a much higher activation energy. Does the reaction consume or release energy when it occurs? If we look here, these are your reactants and these are your products, okay, and it doesn't have a lot, but the products are going to be slightly lower in energy or slightly more stable than your reactants, so it's going to release energy. delta E is going to be releasing energy when this reaction occurs. So the answer is release energy because the products are lower in energy than the reactants. Okay, so that's basically how you would do this, or said another way, delta E is negative. All right, if it was delta H, you would say this is exothermic. You guys haven't learned delta G yet, but in an organic book, this is usually delta G, or G that's over here. Gives free energy that you would have over here, but they use the generic term here, just energy, because it doesn't really matter. But you can't say exothermic because it's not just delta H, and exothermic only applies to delta H. So I hope you found this useful. Good job working on the test. This stuff takes practice, so please practice these problems. There's a lot of ones here where the math is challenging, and even if you have the formulas and you plug in the numbers, it can be challenging to get the right answer, and the only way you're going to get better at it is to practice. So please practice. All right, thanks for watching. Keep up the hard work.